Okay, welcome back, guys. And I hope if you're watching this, it means that you've got the concept down of analyzing piecewise functions pretty well given a graph. And maybe you're just a little scared of the idea of analyzing it from an equation. And here's the deal, everyone is scared of these, okay? For whatever reason, this instills panic in a lot of students. And today I just want to go over sort of, in my mind, the three most important types of piecewise functions that you might be asked to analyze and sort of how to approach it, okay? Or how I would approach it. So the first thing I want to do is just show you one example of a piecewise function that's given and talk through what type of situation this is going to be. Because what we're looking at here is that sometimes you're going to have two pieces of graph that connect. Sometimes you're going to have two pieces of graph that are disconnected, and then sometimes you're going to have a graph that creates a whole. And those are the three most important and actually most common types of examples, okay? So what do we have here? Well, I always approach these things graphically because that makes it easy for me to see and understand what the limit is and what kind of discontinuity I'm looking at. So if we're dealing with something like this is saying that we have a parabola that's been shifted to the right any time for any value of x except 1. All right, so if we want to get an idea of what this looks like, we're going to have our graph here, and I'm just going to kind of sketch this out, right? So it's a parabola shifted right, and it's going to be that parabola, except we are not going to exist on this parabola when x is equal to 1. So what that means is that there will be a hole there. So I'm just going to draw kind of an open circle there. And in fact, it might be good to use different colors. So for this one, we'll use orange for the parabola, and then what it's saying is that when x is 1, it wants you to be equal to this function here. Well, this function is just a numeric value of -3, so that really does mean that it just wants you to exist as a point down here at -3. So what we have here is a graph that has a hole and a point that exists somewhere else. That's actually another way of saying that. That's actually called a removable discontinuity. You've probably covered that in calculus already. Discontinuity. Let's see if I can spell. All right, there we go. So that is a removable discontinuity. Now, that means we're definitely not continuous, right? But let's talk about whether or not we have a limit, and if we have a limit, where would that limit be? Well, from the last video, hopefully once you have a graph in mind, you can analyze the idea of, do I have a limit from both the left and the right hand side? And on this one, if I'm looking, or if I had been asked, hey guys, I want you to find the limit as x approaches 1 for this function f of x, okay? If that had been asked, then we're analyzing what's happening exactly right here. From the left side, the graph is trying to get to 0. From the right side, the graph is trying to get to 0. So because it's coming from both sides, you do have a limit at 0. So if you recognize that the piecewise function is this situation of an equation and a number right here, a lot of times that is going to create this idea or this situation of a hole, and the limit will exist, okay? Algebraically, this also works. If you take that 1 and you plug it in right here, 1 minus 1 squared, you do get 0, okay? So that's example 1, all right? So let's look at another common example. I'm actually going to keep the same equation on the top, and you know what? I'll keep the same bounds and everything, that's fine. And let's create something that's not a number right down here, and let's see what happens, okay? So maybe that was our first equation, and maybe the next equation is like, maybe it's like x minus 1, something like that, okay? And over here, this doesn't make sense now, now that these are both equations. So what would happen is this would become some sort of an inequality over here. So for instance, this one might say for anything where x is less than 0, and this could be anything where x is greater than or equal to 0. And in fact, you know what, I want that to be a 1 still. Let me go back to using a 1, because that was a nice little situation there. 1. Okay, great. So I'm going to do the same thing. I've got two equations, and I've got this breaking point of 1. I just want to see what it looks like and sort of what's happening. And so if I go to graph these, we're going to do the same thing. Let's let the top one be orange. And when I do that, I'm drawing that same parabola. And now instead of drawing the complete parabola, okay, this is a 1, I'm just going to make it stop here. It's not going to show the right side because this says x has to be less than 1. And I'm also going to put a hole here because it's strictly less than, right? It's not less than or equal to. So this is my graph of the top equation. And then at this exact point, this graph is going to pick up, the graph of x minus 1, which we're going to do in blue. Now, the graph of x minus 1 would have a slope of 1, and it would start down here. So it would be here, here, and here. And I'm not going to graph the whole thing because I have to only exist when x is greater than or equal to 1. So it's going to pick up right here. Woo, and then it's going to keep going like that. Okay, so it's like a parabola on the left, and it's like a line on the right. And when this happens, it is two pieces of graph. However, if we are asked for the limit as x approaches 1 again, because they meet up, right? They meet up at the exact same y point. Because of that, the limit will exist, and it will still be 0 in this case. One way you can check that algebraically, if you plug in your 1 right here, 1 minus 1 squared, that would be a 0. If you plug in your 1 here, 1 minus 1, that would also be a 0. So I have students that sometimes get all wigged out with graphing, like, I don't want to graph it again. That was last year. Please don't make me graph it. Okay, if that's you, then this algebra way will work. You know, take your 1 and plug it into both and hope that you get the same number. You do kind of need to know the graph though, because in your next unit you're going to be asked about differentiability, and I'm not going to get into that on this video, but when you're asked about differentiability, it is rather nice to have a graph in mind so that you don't have to do everything algebraically. Okay? Alright, so that's example number 2. Now example number 3 is going to be the same situation, except maybe now I'm going to create a function on the bottom where, there we go, where things might not meet up so nicely, you know? So, in other words, we're going to get rid of that equation right there. And let's replace it with, I don't know, how about something like, maybe something like, you know, negative x plus 3 or something like that. Okay, so if this is our new equation now for the bottom equation, I have negative x plus 3, and that's going to pick up right here. So I want to graph that out and see what's going on. So 1, 2, 3, and x plus 3. Okay, so it'll be like here is where it would pick up, and then maybe it'll be there, and then maybe it'll be there. Okay, so it's going to look something like this, okay? Now, this one is a filled-in circle. This one would be an open circle down here, so if you don't like that light blue that's filled in, you can go back to making that sort of a hole right here. And let's think about the limit now as x approaches 1, okay? So if we were asked to do that, limit as x approaches 1 of f of x. Well, the thing is, now, just like the other video, when I'm approaching this x value of 1 from the left, you can even kind of dash it if it helps out, then I'm trying to get to 0 from the left. So from the left, it's 0. But whenever I'm approaching 1 from the right, it looks like it's up here at 2. and these do not match. And since they are not equal, then the limit also does not exist. The overall limit as x approaches 1 will not exist. Now, could I have done that without graphing it out and going through all that? Probably so. If you would like, you'd take this 1 right here, and since 1 is where these two end up, you could have plugged in a 1 here and gotten your value of 0. You could have plugged in a 1 here and got your value of 2, and seen from that oh wait, those two values are not the same. And then you could have said, oh okay, I guess the limit does not exist. But once again, I want you to have a visual for what's going on, and I make my students graph them out. If your teacher doesn't, then they're nicer than me, but maybe this helps out. So there's your 3 different cases. You've got a jump discontinuity, in which case the limit does not exist. If there was a hole from earlier, the limit does exist, and if the 2 graphs meet up, yes, the limit still exists. So good luck to you with analyzing these. Graph it out when in doubt, or use your algebra knowledge and try to figure out if this thing's going to have a limit.